Okay, well, thank you all for coming, and welcome to part one of our two-part mini-series on quantum computing. Um, so this is part one. It's a practical guide to quantum technology for patent practitioners. Um, and in a few weeks, we'll be presenting part two, which will kind of this one is going to mostly provide a technical overview of all the different parts of the quantum technology stack. Um, and I think we're going to be I think regardless of your sort of technical area of practice as a patent practitioner, I think you're going to find something in this part one today where you're going to start seeing aspects of this technology filtering into, whether you're in mechanical or electronics, photonics, software, uh, you know, cryogenic systems. You're going to start seeing aspects of this technology cropping up in your practice area, and we want to kind of give you a preview of that today, and a few tips for how to think about that in terms of IP protection. And then in a few weeks, we're going to have part two of the mini series in which there will be more detailed tips for drafting patent applications and sort of patent strategy for trying to protect some of these technologies for your clients. So I'd like to introduce our speaker for this mini series, Dr. Laura Kinnischtzke. She has her PhD in physics with a focus on quantum optics, so right on the money. She is our resident expert here at SLW on quantum computing. She is a patent agent working with our clients on a bunch of these technologies. She'll be leading you through the webinar today, and then if you're back with us in a few weeks for part two, she will also be leading that webinar. And so what we're going to do for this one, Laura will be handling the presentation, and we will have the chat window available if people have questions or comments. And if you have questions about a specific slide and you want to have us address it before moving on, I'll be monitoring that, and I'll find a time maybe to sort of jump in with those questions. But we will leave a few minutes at the end for a Q&A, which will also be, you can just put your questions right into the chat. And we'll try to address those at the end. Well, realistically. So, Laura, without any further ado, why don't you take it away?
Thanks, Matt. Yeah, so just to start with an outline, quantum technology covers a broad range of existing engineering disciplines, but with a twist. So I wanted to start out with some quantum mechanical concepts and kind of the four that show up in these technologies, and just to kind of give a framework and a vocabulary for as we get more into what the technology actually is. We'll briefly touch on quantum communication systems, as well as quantum sensing and metrology. And then the main, most of the time we'll be talking about how do you build a quantum processor? How do you do computing with these quantum mechanical concepts? What does that look like with hardware, and what kind of software and applications are there? And since this is a very broad range, we're not going to be going into too much detail in any one area. So for particularly like computing, there's a lot of different frameworks. There's quantum annealing, and so I'm just going to try to keep it at a fairly high overview level to give you again a sense for the range of engineering disciplines that are being brought into these quantum disciplines. So with that, our first quantum concept is superposition. And so a quantum entity that can be an electron, an atom, a photon, quantum entity can exist in a linear combination of states. We can use this notation, it's called Bra-Ket notation, comes to us from physics, and usually we think about states 0 and 1. These are abstracted, obviously, from something like a photon, where 0 and 1 could correspond to polarization. So that would be like a horizontal polarization and a vertical polarization. And again, if we're going to talk about an electron, that might be 0 and 1, might be spin states. atoms, it might be different um, electron orbitals. So these, if you see 0 and 1 throughout, you can keep in mind this is already one layer of abstraction from the physical system of what's happening. And this the state of the entity is psi, so we call that a wave function. So that wave function is going to evolve according to the Schrodinger equation, and solutions of that can be looked at as a linear combination of these two basis states. The values alpha and beta are probability amplitudes. So this is kind of where we start getting into quantum mechanics different from classical mechanics. This wave function is um, not the physical object. When we do a measurement and when we try to access the quantum information, we're going to deal with the probabilities of the system, which is alpha squared and beta squared. But alpha and beta are how the wave function is going to evolve. And one way to think about the wave function, and it's very useful when thinking about qubit and qubit superposition, is on this concept of a sphere. It can be the Bloch sphere, or actually comes from magnetic resonance imaging, kind of the first use of electron spins. And so you can see we just start out by mapping our 0 and 1 states. You see they're kind of orthogonal along the z-axis here. And then in this XY plane is where we can kind of talk about a superposition. And you can think of the state psi as having sort of an angle, an azimuthal angle, and a polar angle from the z-axis, a combination of x and y. So those are just different mental models we might refer to. And just as a reminder, when we're talking about classical information, classical bits, it's very deterministic. It's 1 or it's 0. It's not this kind of probability that evolves and we have to collapse it and all this stuff. So just again, getting a flavor for how quantum we have to rebuild our whole architecture in some ways. The second,
Laura, actually, we actually have a question, and I think you just sort of addressed it, but
yeah,
the question is just sort of I think a question for some broad context.
yeah,
The question is, could you start by defining the word quantum and its use in this context?
yes.
Maybe more generally, just what when we talk about quantum computing generally, as opposed to classical computing, what are we talking about?
Yeah, right. So quantum technologies are going to maybe go back to kind of this slide. So even communication or sensors or computers, um, there are the things we interact with every day are macroscopic. They evolve according to um, classical mechanics, so Newtonian, if you remember kind of force diagrams, or some statistical mechanics, thermodynamics, those are all kind of classical domain in the physics use of the word classical. And when to um, quantum mechanics, just maybe talking about the history will help too, was kind of in the early 1900s. There were some problems with these classical statistical models, and their concept of the photon was initiated around 1904. And then we got kind of electrons and particles and how does an atom work. So to when we're describing a quantum entity, it's something that is not going to be like an everyday type of object we're looking at, and we actually have to go through a lot of work to isolate the everyday object and access that quantum property of it. Does that kind of answer?
Yeah, that's great. Thank you, Laura.
Okay.
Jose also has pasted in I think a definition here in the chat that
Sure.
also people want a
Yeah.
little more resolution. That's great. Thanks
Right.
for that.
Yeah, thanks. And with all this quantum business, there's the next concept I wanted to point out. It actually comes from classical, just mathematical techniques as well. So the concept of interference, any system that has wave-like behavior, could be water waves, be acoustic waves, can combine by adding the waves. And if they're in phase, as we see here, this purple one and blue one on the left-hand side, and we just kind of plop those two, waves together, we can get constructive interference where the resulting behavior is amplified. And if they're out of phase, we get destructive interference where the actions cancel. And this interference shows up in quantum entities with that wave function. So that's where this operator psi or the state psi is what carries the wave-like behavior. And again, it's really not intuitive because this is exhibiting wave function in a way that we don't directly observe. We only observe the effects of the wave function when we measure it. So when we get these alpha and betas. So there's going to be some things like this next idea of decoherence. Decoherence is a loss of quantum coherence. Okay, what does that mean? It means that this wave-like property of the quantum system has collapsed. And again, a lot of this terminology I've inherited from physics. What is wave function collapse? We don't need to get into kind of the Copenhagen interpretation and all that. So physicists are still philosophically defining things like wave function collapse. But in the context for quantum technology, decoherence is a very important concept because it's basically an amount of time you have to manipulate the quantum system before it has interacted with its environment and lost that wave function behavior. And so it just becomes like a classical particle statistical ensemble rather than quantum superposition. And in particular for qubits, when we jump ahead to quantum computing, decoherence lifetime is usually what it's called, is an important benchmark for when you're thinking about making gate operations on a qubit and different things. You want to put all your gates in a coherence lifetime. So again, just trying to, in the mental model picture, you can think of it as when the system has coherence, I am able to take this vector, this yellow arrow, and the spot on the sphere, and I can move it around. I can control it. I can put it where I want it to be. And when it's decohering, it's either not responsive or just I personally like to think of it as like this arrow has sort of shrunk all the way down and doesn't even exist anymore. It's just a particle, just a classical thing. So yeah, with that, the last quantum property is going to tie into the first application of quantum communication. And so probably you've heard of entanglement in some fashion in maybe sci-fi or different, in reading about quantum effects. It's what kind of the most mind-bending property I think that we'll talk about today. So when I take, so far we've been talking about one quantum entity, and there are certain ways that you can have two quantum entities interact. They have this property, we'll call it entanglement, where the quantum state, that psi quantity we saw earlier, of each particle cannot be described independently, even when these two particles are separated by a large distance. Mathematically, we usually notated in some way by having sort of two objects next to each other in this bracket. So if you think about when we had zeros and one, for one quantum system, there was two basis states, and now we actually have four. So we've grown our state space now there's four probability amplitudes that we could have, and you can kind of start to see, oh yeah, I could see why this could be helpful for computing because now I'm storing more information when I entangle two things together. So it's just, again, jumping ahead a little bit. How can we use entanglement? So the photons are a nice way to think about entanglement from my background and perspective, because we can create entangled photons in nonlinear crystals where if you shine laser light in intense enough, you can get out two photons that have sort of correspondingly opposite polarizations. And you can use that in like a quantum key distribution. So key distribution is for secure communication across networks. The quantum part of it is using this entanglement piece. So what you would do for quantum key distribution is Alice would start with two entangled photons. um, she would keep one and she would send the other stream to her key receiver. Alice and Bob are kind of the quintessential characters that are usually reused in this example. And then, so we have these quantum objects. What do we do with them? So Alice and Bob are going to, according to a certain protocol, have measurement devices. For photons, you usually use a polarizer and a photon detector, like just like a photodiode or some such. And Alice would do a series of measurements, and Bob would do a series of measurements, and then they would compare. And if their comparison is like, I measured up and the detector didn't detect it. I measured down or I measured horizontal, vertical, 45, all those different range of angles of polarization, recording when you have signal at your photodetector. And now you have two data sets. You have Alice's record and Bob's record. When they compare, the result of that comparison will tell them if the entanglement was preserved in their photon streams or not. And why would it not be preserved? When somebody attempts to read the photons, so any measurement process, whether it's intentional for Bob or whether it's somebody who is trying to intercept, is going to destroy that entanglement. So that observer effect is really powerful for something like secure communication. Um, so how are we doing, Matt? Any other questions?
No, no, this is great.
Okay. So as I said, with quantum communication and particularly quantum key distribution, we're going to leverage that effect of entanglement is disturbed, is destroyed. If there's an observer attacker in the middle, any attempt by an adversary to eavesdrop irreversibly alters the entanglement, the photon states, alerting users to the intrusion. Um, very fortunately, for quantum key distribution with photons, we have some telecom infrastructure with fiber optics and cables. So we do see some of the same problems. The engineering challenges here is photon losses in a standard optical fiber add up over long distances. Again, this is a known thing from photonics engineering, from telecom communications, and now it's showing up in our quantum systems. It's just maybe the first of many times where we'll kind of point to engineering problems that you don't have to know, you don't have to be as well versed in maybe in all these quantum concepts to bring some engineering to bear here. And where the quantum twist comes, though, in this problem is that um, amplifying the light in an entangled state is non-trivial. So you can't just sort of take one photon and put it into an amplifier and now you get 10 back out. Those 10 output photons are not going to be entangled in the same way. So we're going to now create something called a quantum repeater or even quantum memory, which is like a whole different thing. Something called entanglement swapping to sort of chain entanglement from one physical location to another physical location before you have too many losses add up. So again, we have some engineering that it has existed before with maybe a quantum twist to it.
Or we do have a question actually about the PKD example. So um, here the question was, when someone observes, eavesdrops on the communication, does it interfere with the intended communication?
That's a good question. I think that goes towards thinking about the QKD system overall. I think it's more like you are alerted to the fact that there's someone listening. If you were, and from again, what I understand, how a QKD system would be deployed is to first establish the secure communication, do that key exchange, but then you're not going to probably continue using those entangled photons for the message that you want to send. So by using the entanglement at the beginning or, periodically throughout the communication link, then you can know if there's somebody else listening. So you're kind of like creating a communication channel that has quantum entities on it, but you can still send classically your standard communication. That's my understanding. Again, this is like broad overview, so we're kind of testing the limits of my knowledge of how these systems are deployed. But that's kind of my understanding.
Great. There are a couple of more questions, but I think I'm gonna just
Okay,
why don't we keep going and
sure.
maybe we can work them in later.
Yeah. So the second area where we're going to deploy some quantum technology that's not computing is for sensing. So I've kind of been mentioning these quantum properties are very sensitive. We have to isolate from the environment. We'll see that even more in a few minutes with how a quantum computer is actually built. And instead of sensing, quantum sensing says, instead of seeing that as a negative, can I somehow turn that sensitivity into a data point, into a signal that tells me, oh, my quantum system was disturbed by an electric field. There must be an electric field present. Where is it? What frequency is it? What strength is it? And so you can have, especially for certain like alkali element material, like rubidium and cesium and those kind of optical clock atoms, you can use them for sensing things like electric fields, magnetic fields, um, even gravity and temperature, different things. Gravity is a really interesting one because it's like, well, who would want that as an application? Oil and gas, right? Because you're going to be, if you can sense really minute changes in the pull of Earth's gravity, okay, that's because there's a different material, density of material, different things. And the point here is that each sensor is really unique to the sensing application. And you're going to, again, see similar to the QKD example, there's a blend of the quantum aspect of the sensing system, but then it ties into other classical computing, control system, data recording, data processing, different things. And one of the big advantages or reasons why you might invest in creating quantum sensors is for smaller form factors and larger dynamic ranges. All right. So with that, we're going to start to take a big bite on the quantum computers because it hasn't been complicated already. And so we've already touched on the fundamental unit of a quantum computer is going to be that superposition a qubit. In classical computing, we have a bit, right? We have something can be a transistor, can either have a charge there or not have the charge there. In a qubit, we have this probabilistic state mathematically that we're going to be manipulating. Again, why are we going to try to build a quantum computer? Computational power scales linearly with the number of transistors. Quantum bits, if we can get them to work, it scales as 2 to the n. So it's a big speed up. It's parallel processing. It's you know you can certain problems can have exponential speed up, and we'll see that again towards the end. Um, like one of the main messages here for the whole webinar, quantum technology is not a single monolithic invention. It's a lot of different technologies that are coming together that seem maybe distinct, but are going to be combined to make a quantum processor operational. So our first maybe point out to the audience as IP practitioners, To draft and prosecute effectively, I find it very helpful working with clients to identify which layer the invention occupies. These the engineering that happens is so specialized that a person who's working on a new qubit design is not going to be working also on an analog converter or a control system. So you have teams of electrical engineers who are being deployed who don't understand maybe the qubit physics, but who understand how to, shape waveforms and have high transfer speeds and different things. So their expertise is being utilized, and the same thing for kind of software layers as well. So it's maybe not obvious at first that this would be the case, but once you start maybe interacting with different clients, you can start to see, okay, this is where they this is the problems they're solving, or within their large quantum division, I'm working with a team that is at this layer of the quantum computer. And just again, kind of helpful to orient, is this going to be more towards a method claims or system claims, or kind of how can you reuse your existing experience? So as I mentioned, it's a big stack. So we're gonna kind of walk through each of these with, again, various levels of um, detail, trying to not overwhelm with too much knowledge, but give again, a sense of what's out there. Um, so there's software and applications, algorithms that are focused on quantum operations, quantum logic operations, as well as software for control, software for routing and kind of helping the quantum processor do the computation. Um, Error correction is a very big and necessary component to quantum computing, especially right now. We'll touch more on that later. Control systems and enabling hardware kind of go hand in hand with what type of quantum register you're going to choose. So we'll kind of see those show up together. But then again, the quantum register is going to be how are we physically constructing a qubit? So that's going to be what materials, what chip, are you using silicon? Are you using superconductors? Are you, there's even some CMOS fab that can be done. So with that, so we're going to start with the hardware layers. So we have here kind of a cartoony image of a superconducting quantum computer. So our quantum processor is going to be some sort of chip. So probably superconducting layers, superconducting circuits built on top of silicon, packaged and housed at this millikelvin stage of a dilution refrigerator. Dilution refrigerators have existed as research equipment for quite a long time, but in order to be deployed for talking with for use as a housing a quantum processor, you need some improvements there. So why do we need the dilution refrigerator? Well, sorry, we'll talk about that with superconducting in a minute. The thing I wanted to highlight here is just the number of different systems that are interacting to create the whole picture. It's not just I'm going to take a quantum processor and plug it into my laptop and now I can do quantum computing. So that was just kind of the level message we wanted to get across here. Okay. Okay. So I touched on this a little bit. So there's many different hardware modalities. We're going to look at 5 different ways, 5 different platforms to build a qubit. Superconducting circuits. IBM and Google are well known for this, for their efforts here. You can use, again, silicon as your chip material. You can do some lithography, maybe not like a streamlined CMOS process, but existing systems. But as we just saw on the last slide, it requires the bigger system requires extreme cryogenics. The next hardware modality is trapped ions. So Quantinium and IonQ are two companies that are building systems with trapped ions. I think Quantinium has had some news press releases lately about their recent chips. Um, so this is individual atoms, and you're gonna essentially build a chip to have some electrodes that trap the ions like in a line, and then you do your manipulation from there. Neutral atoms are somewhat similar in that they're atoms. Instead of a chip, we're gonna hold them in place with lasers and optical tweezers. So that's pretty kind of different twist on things. Continuing with light, we do have some photonic uh, qubits, as we mentioned, photons with polarization or path, which way type information. You can use the entangled photons to kind of carry your information that way. And the last one is spin qubits. So if you have a single electron transistor, you can trap a single electron and then use that spin to carry the information. So digging a little bit more into superconducting circuits. So that's okay. So superconducting, uh, we can start to see why we need the cryogenics. We know, you might know, we don't have any room temperature superconductors. Most materials are very low temperatures to get to be superconducting, and even above that to create this nonlinear energy level and isolate the qubit state. So really removing a lot of thermal energy from the system is why we need those cryogenic temperatures. So Josephson functions are the basis of the superconducting circuit qubit. They come in lots of different designs, lots of different flavors. The image I have on screen here is from a patent shown, the number shown below. And the qubit portions are this 4021 and 4022, and then there's some sort of coupling in between. So if you're interested, you can go look at the patent, or again, we don't have time to maybe go into everything, but part of the coupling and these other traces on here is to deliver microwave pulses. So once we have our 0 and 1 states, to do any sort of that manipulation of information, we're gonna do our rotations with microwave pulses. So some of the challenges for superconducting circuits, and we won't go into this much detail for every technology, but it is probably one of the most, I don't want to say mature because the other ones are also very, anyway, to me, it's the most well-known platform. You have this wiring bottleneck. So we saw before that dilution refrigerator, there's only so much space, and the more lines of coaxial cable you add, the harder it is to keep that low temperature. So thermodynamically and even space constraint wise, there's like, how do you just put that many cables, right? If we're going to create a computer, we want a processor, we want lots of qubits, but I need lots of wires to talk to those qubits. Some of the engineering, again, is kind of creating, creating circuitry that would basically have your qubits on one chip, create a whole second chip, CMOS chip for control, bond those together, and now cool that system down. That requires things, so 3D integration, superconducting through silicon vias. That's really cool, right? And through silicon vias, again, is a concept that comes to us from, Intel or silicon manufacturing now for some time. So you can kind of start to see how reusing engineering concepts, tweaking them for quantum peculiarities is again one of the themes we want to maybe put out there in this webinar. Our next qubit platform is trapped ions. So individual atoms are stripped of an electron, electromagnetically suspended in a vacuum, and manipulated via lasers. So in this patent image, the ions that are being manipulated are this 102, these 1, 2, 3, 4, 5 ions. There you can see this block is like a classical computer that's being used, the kind of the control system of an acousto-optic modulator. The acousto-optic modulator will turn on and off these laser beams that are coming in. The laser beams 110 will then talk to these atoms. The atoms fluoresce, the fluorescence is collected and detected. PMTs, in some examples, photomultiplier tubes. Um, so that's kind of the collection of technologies that would be used in this platform. Some of the innovations are for kind of scaling up these detectors. So maybe something like a quantum CCD. There is some utility in being able to physically move the atoms around. Again, having to do with how the logic of the information, what it means to use this as a qubit. And again, that's kind of too detailed to go into for each system here. But as you can see, there's lots of laser beams that are used, even just for a 5-atom, 5-qubit ensemble. So complex optical delivery systems are going to be very useful. There's a lot of optical engineers in the world, so there we go. Neutral atoms are also going to use light again. This time you're going to use light not just for the fluorescence and the gate control, but to actually hold the atoms. So instead of electrostatic, electromagnetic RF traps, we're using focused lasers. This image is from, so each of these circles is an atom, and then the sort of like on and off color, the black and white is kind of like their physical arrangement, and then there's like doing qubit operations. Again, this modality is to implement the gates, which is sort of what's shown here, left to right, kind of implementing a computation using this geometric arrangement of atoms. Relies on the quantum physics of how the atoms can be have this Rydberg state. It's highly charged, and then there's going to be some aspect of how it interacts in the grid and different things like that. The qubit states are going back to those atomic energy levels or Rydberg related states. So moving on to continuing with light. So now we're just with light, photonic qubits. We're encoding information in the polarization or the path of the photons, relying on measurement-based quantum computing. So this is, again, a little bit different architecture than being able to, you can't really manipulate a photon without destroying it, as we saw before. So how do we kind of create computation when we have that restriction? You have to use really large cluster states. So you can do it, you just need a lot of photons, and you need to arrange them very cleverly and do lots of different photonic manipulations on them. So what I'm showing here in this slide is these are lenses and beam splitters, detectors, kind of what we would see for macroscopic on our optical table. But each of these elements has a corresponding device on a photonic integrated circuit on a photonic chip. Again, reusing that engineering and technology for photonic computing purposes. Similar to quantum key distribution with photons, we have lots of loss is a big problem. Getting the photons, losing the photons, keeping track of them, it's a big mess. So that's the issues with photonic qubits. And the last one is silicon spin qubits, which are a little bit still in the research lab phase. but here you're going to take like a single electron transistor and fabricate that on really, really pure silicon. And then you can use that transistor to load an electron and manipulate it with those electrical gates. You don't require light for this one. It is very compatible with CMOS foundries and CMOS processes, with some caveats that the performance of the qubits might be restricted or have to do like additional purifying or cleaning processes to really pay attention to the kind of like background impurities in the devices. So with that, those are all of our qubits. We still have a lot to cover. Just wanted to encourage again that looking at each of these qubit platforms, there's been associated hardware and engineering challenges to cover. And there's a lot of intellectual property associated with those engineering challenges of, you can think about it as either adapting an existing technology for a quantum flavor, for a quantum twist, or solving the issues brought forward by the quantum devices with with the modifications to existing technology. So kind of either think of it from either direction. So with that, we're going to move into a little bit more of how how do how does computation work? What does that even mean? Um, Again, trying to keep this at a high level, and also this is not my particular area of expertise, so um, just keep in mind this is uh, might not be accurate for all types of computation or whatnot. But generally speaking, right now, as we are today, there are quantum processors that are online, and so this phase of technology is considered in the industry noisy intermediate scale quantum. And the scale referring to the qubit side, the qubit number of qubits, and also, as we'll see, the number of logical qubits. And the error correction is a necessity, but we don't have enough error correction or enough qubit quality to run really deep algorithms. We can run some algorithms, but we're still kind of designing circuits, designing algorithms to really push the processing power to what would be considered fault-tolerant quantum computing. So we need larger qubit counts to support algorithmic redundancy to be able to apply lots of quantum gates and run the algorithms. So why is error correction required? Qubits are inherently unstable, as we saw from the beginning. Decoherence, that concept of decoherence really plays a big role. And as we saw with quantum key distribution, when you observe something, when you measure something, the state is destroyed. So I can't copy it and paste it and paste it and paste it. I can't reproduce the information on demand. And from the world of error correction, as it exists for classical computers, for your CPUs and your GPUs, there's a lot of language that is reused and concepts. So I just wanted to touch on in that mindset the errors that would occur in a qubit could be considered like a bit flip. So bit flip going from 0 to 1, or we have this again concept of a phase because we're on this sphere and I can move this qubit, this vector around. So you could also imagine that phase flipping, this angle flipping along one axis or another axis. So that again gives some more complexity to this what types of errors can occur. So some of the So what I understand about quantum error correction, which is still at a very basic level, is that we're going to build a logical qubit and run our algorithms using the logical qubits. We're going to spread out our quantum information across 100 to 1,000 physical qubits. So if I am so in this graphic, for example, so it'd be like a surface code representation of the nodes being qubits, and then there's connections between them, and the colors mean something, and you're going to measure some of them, and you're going to not measure other ones of them. And then that's going to allow the logical qubit state to evolve in the way that you want the computation to proceed, but you're not going to destroy the quantum data. Key point here is that it may take hundreds or thousands of physical qubits to create a single reliable qubit. And there's lots of different quantum error correction protocols, ways of doing the measurements, techniques, and ways of mitigating errors during computation. So this is a fairly active area. And again, it starts to get to if you have experience as a practitioner with algorithms, with software, they're very mathematical driven. But so you might want some experience there, but you don't have to understand the hardware platforms or the quantum basics to really understand, okay, we're going to be doing some manipulation of information here. So that's the key point there. So I've mentioned quantum circuits a few times, and also kind of indicated that physical qubits or logical qubits follow a prepare, evolve, and measure sequence of operations, generally speaking, with that's very, very high level. Some of the gates, some of the qubit operations that we can do are they have a matrix representation, they have a rotation representation, they have names, Pauli gates, a Hadamard gate, which creates an entanglement between two qubits. That's what is shown in this picture here. C0, controlled Z, swap, Toffoli gate. So these are all sort of well-defined sequence of operations. And then a quantum circuit is going to be a combination, a choreographed sequence of these gates to start doing the computation. And one thing I wanted to note here, which we'll probably cover in more detail in our next webinar, we're starting to talk about method claims, right? When we're saying applying gates or a sequence of events. And this, even though we're somewhat abstracted to this quantum register with these boxes and lines on it, it still corresponds to physical actions of shining a laser, sending a pulse to a qubit. So we're still pretty, not too concerned about abstract concepts here. These are physical actions that are occurring in a method sequence of events. So two algorithms that you may have heard of with respect to quantum computing. The first is Grover's algorithm, and that my understanding is these algorithms can apply when applied to a quantum computer. There is a speed up over classical processing, but problems such as unstructured search and factoring are problems that you encounter with regular processors as well. So these are algorithms that would highlight the advantages of the quantum processing system. So Grover's algorithm will apply a diffusion operator to iteratively invert and amplify the amplitude of the target state. So this technique of amplitude amplification has kind of cropped up and stuck around, could achieve a quadratic speed up for database searching. And another one is Shor's algorithm for factoring. mapping the factoring problem to finding the periodicity of a function, and then using a quantum Fourier transform to create massive constructive interference at the reciprocal of the hidden period. And so you can kind of identify where that periodicity is and um, go backwards from your ancillary function there. Um, this, again, you might have Shor's algorithm pops up when talking about cryptography. So RSA public key cryptography is there's a lot of work slash concern about when a quantum processor can reliably run Shor's algorithm. Any RSA public key cryptography, public key encryption system is going to be obsolete. So how do we do cryptography after that time? So there is kind of a threat vector or challenge there. Again, if you work in cryptography or encryption, you may be aware of this, but another area that kind of dovetails with what your existing experience might be, and you might see quantum computing crop up in that area. So with that, so a few minutes left. I'll maybe really quickly breeze through these. Um, so the kind of software that we're going to deploy or is going to be for just operating the quantum processor, um, hardware access and physical control, all the way to software development kits and domain-specific problem formulation. So you're going to be, you can be a quantum developer and, talking in a Q-sharp language, writing programs or a Python, or you could be, writing error correction algorithms, lots of variations. So software development kits allow programming via familiar abstractions like Python or Q-sharp, a specialized quantum language. So again, you're going to be using software to create these quantum circuits. So this is just another diagram of a quantum circuit. There's three well-known structural libraries to build out quantum logics. And there's certainly a lot of area to automate some of this synthesis and do sort of optimizing the circuit logic at this level. Compilers are required for a quantum processing unit. Every QPU, even within the same platform, will have a unique physical layout and various connectivity between qubits. So a compiler is needed to map and route the quantum circuits that we have designed to fit a specific hardware graph. Also, for building those logical quantum circuits, for routing, mapping, assigning specific physical qubits to various logical qubits, and gate scheduling. So scheduling, talking to the controllers, talking to the analog pulse generators to generate those analog pulses at the right time and sending them to the qubits at the right time. Again, all of these, I think on this slide in particular, there's not very much that's going to be quantum specific. You may know or have already drafted and prosecuted software that has these types of operations happening. Quantum simulators are classical software that mimic quantum behavior. So if you're a quantum developer, you're building quantum circuits, you want to test them out, verify your logic, but you don't want to burn expensive QPU time, you can use a quantum simulator. And how do you do that? That's, another kind of engineering problem, a place for innovations to happen. So we haven't touched on this maybe in an indirect way, but quantum computing, quantum processors are not currently thought to be deployed this way a laptop or a smartphone might be. And so for who's going to use the processing power, people who already use high performance computing services, which are often available through the cloud. So you want to make some software that allows an end user to just access that quantum processor through the cloud. And since you're doing that and you have cloud resources, you can also offload some of the data preparation, input, output to different uh, classical cloud instances within there as well for some division of labor. And in particular, there you can even start with that in mind to design your algorithm specifically to run in a quantum classical feedback loop. Uh, so lastly, again, who is going to maybe be these first users? Chemistry and material problems are very well suited. Chemistry is one step away from physics in our hard sciences. So you're going to be doing molecular simulations, which can inform drug discovery, battery design, finance. Um, I know a lot of quants who were once physicists, so there's lots of heavy math that is in the finance world that can, again, the the speed, increased processing speed for certain problems is where the financial analysts are going to be interested. And then logistics, this one kind of surprised me a little bit as well, but just it's complex multivariable problems are gonna, probably take advantage of quantum processing in some way, again, probably with some cloud instances. So with that, quantum is a stack, lots of different hardware, need error correction, and probably something you have worked on in your engineering or legal career will have a quantum counterpart or quantum flavor corresponding to it.
Thank
Matt.
you, Laura. That was a tour de force. That was a real fire hose of information, and I think everyone's very impressed. Some kudos are coming in through the chat. But yeah, this is just there's so much going on, so many different technologies. Almost anything um, is either going to be on the design end or the application end, or both. Um, if people do have questions, please drop them in the chat. And also, I hope that people could come back and join us in a few weeks for part two, where we're
Mhm.
going to be diving into really more of the specific tips for patent practitioners, um, as these technologies continue development.
Yeah, and just to tag on to that, if you have anything that occurred during this presentation you want us to address in that practitioner segment, feel free to email Michelle, email our marketing team, or questions that may develop offline. Yeah,
Yeah, please, any suggestions for stuff, we can roll stuff into part two of the
yeah,
presentation.
yeah. So
Things
there
that
is one question I'll answer. I got the
right.
chat open here too.
Okay.
Mitch asks, where do we see quantum and AI interoperating? And I will say that there are research groups working on machine learning on a quantum computer or using like using a machine learning as it's deployed today to help us build a better quantum computer. So there's kind of both directions of
Mhm.
if I have an engineering problem, can I use machine learning to solve it and apply that back to my quantum system? Or, can I run an AI on a quantum computer? There's people asking those questions every day. So yeah, hopefully this overview gives you enough interest and background information to go read um, read more about that. Will it be possible to do quantum computing far above absolute zero? Possibly, but you're always going to need some sort of extreme environment. So in the example of trapped ions and neutral atoms, they do not necessarily have to be at low temperatures, but they do need to be in ultra high vacuums. So you're going to always have them in some sort of isolation chamber And that's why having lasers there to talk to them is really helpful because you don't need as many interconnects and things into those vacuum chambers. But in order to access quantum properties, you do have to isolate from the kind of big macroscopic world in some fashion. So it's going to show up in different ways.
Just a quick note that if people do have more questions that are going into the chat, if we don't get to them today, we'll try to roll them in and address them in part two.
Yeah. Um, so I guess last question, can you comment on quantum materials used in quantum computing or quantum sensing? So I'm not sure specifically what direction to take that question other than um, there's existing research on how to manipulate quantum objects or create quantum objects. So if yeah, you want to be able to manipulate, prepare, read out. So th those are some considerations for how to um, which material selection you're going to use. So it really comes down to material science problems or atomic physics type problems when you're looking at the maybe baseline materials. So
Laura, thank you again. That was a really tremendous presentation,
okay.
and looking forward to part two.